Hello, everybody. My headphones aren't on, so I'm gonna get us going here in a second and get those charging. Hello, hello. Can everybody hear me and see my screen okay? See the video?
Yep.
Okay, thank you very much. All right, so let's see how well this works. A little choppy today, isn't it? Why are you being so choppy? Wonder why it's doing that. Go figure. Try this. My phone's being weird. Yeah. All right. Well, we switched networks. Let's see if that helps. Oh wait. Oh, that's a little better, maybe. Yeah, that's smoother, isn't it? Okay. Hello, hello, hello. All right, you guys can hear me and see me. All right. I'm gonna try walking around here. Hopefully, we don't get too much slow down here. All right. So, what's that?
We're good to turn it on.
You ready to turn that on?
Yep.
Oh boy. All right, we're doing some devilish things here, guys. So what we're doing is we're going to try to hook up temporarily our system over here. So we're going to just review. So what we've got is a wire here and a wire here coming from a solar system outside. All right. So now we're going to make sure you don't get these confused,
Yeah,
right?
I made sure that they're going where they're going.
Okay. And then we know that we're going to have power coming through this. So you've got only one that you're concerned with. So which one is you? Trace that out. I got this camera.
This one?
Yeah. Which one is this red one right here?
I was trying to trace that earlier. I couldn't.
It should go to one of these breakers.
It goes down.
And what's the battery? The battery cable is still, that's off. Treat it like it's hot. Okay. Is that it? Well, it should be going through this. And then we've also got the PV wire going in here. So,
Oh, it's hard to tell which one's which.
yeah, I don't want to turn theirs on. So let's just turn one of these on. Let's just see which one of these comes alive. See power, and they're not going to unless we. Okay, just be careful. Yep, we're going hot.
Top one came on.
Top one came
Yep,
on,
we're good.
which is you. So that is the top one. And so this is your PV power too. So when we turn this on, what we need to measure over there with the meter is, do we have voltage over there?
No explosions. That's good.
Yeah. That's all right. We turned some stuff on over here, guys, so be careful. Nothing that wasn't already hot. Okay. Looks like it's still streaming. That's good. All right, so now we're over here at this box, and what we're trying to do is, I don't want to do that. Go away. All right, we're trying to do a little bit of testing here. So we're going to get a meter. We're going to see if we got voltages here. We should have a battery voltage, and we should also have a system voltage. PV. DC. Yep.
I guess this color don't really matter.
120 DC. Yep, that's your PV voltage. Now test your battery voltage. Should see. Okay, and nothing because we're probably off over here. So we're gonna go fire this puppy up. We know that we got solar system over there now. So we're going to turn this on and this on. She's alive. There we go. Okay. On business. I'm gonna go turn the grid on here. You're hot. Fired up. All right, you're already on. Grid's already on. Okay. Now be careful. So now we should just go through this language selection and see if we can't get this thing to make some power and backfeed it to the grid. All right. I'm going to let you just think about this for a minute, and you're going to run into some problems.
Yeah.
Let me know. There's that dang password
Yeah,
again.
see, it's just like enter, nothing happens.
That's what I was afraid of.
I'll find it eventually.
Is there a battery in there? Pull that out and look for a CMOS battery, and let's pull it. Eey.
As far as I can go.
That just comes out entirely?
I think so.
Oh, God.
We're through a real quick before we pull it
Yeah.
out.
Yeah. That should just come off. I don't know why we have a password. See ya. Okay. I'm going to turn everything off, Strauss. Be safe. Back down. It's all right. Now we know we got a password issue. So what we need to find is a CMOS battery. Pull that battery if I can't find that password. I'm going to turn him back off, okay, guys?
Yeah, we just.
Okay. All right, you're all dead again, Josh. Okay. All righty. So we got to figure out how to get that password out of there. And if you can't find a CMOS battery, you might have to get online and try to look it up, how to reset that password. But usually, I don't know why it would have one, but usually there's a battery in there. It shouldn't even have a CMOS battery. Okay, carefully. Part of what we got is you got your wiring in it still. You take your wiring out and your cables out, you can work on this. See what you got. Yeah, there you go. Pull those back out, all of them. Your batteries should be dead. Yeah, we got to check here. So there's off. There's off. Okay, everything is off. Over here.
Can you measure real quick, just to make sure?
Yeah, always measure. I don't know if we've got a battery in there or not. You may not, but if you see a watch battery, pull it. And that'll clear a password.
Is that what I'm looking for?
Yep, like a watch battery. Okay.
3.5 volts.
You found one?
I'm getting 3.5 volts on the battery.
That shouldn't be anything. That's a 48-volt system. And you got all your breakers off anyway. So those breakers are going to it. Yep, right there. Breakers off. Okay. Question?
Point where I guess I need this switch and these ones here, and then I can plug these in and I'm done. But until I get them, those disconnects, because these two up here.
Well, you can bring those in. Those are your power cables.
Okay, because they go to this switch here.
Not necessarily. We're going to match what we got over there.
Okay.
Okay? That's really all you really need to do. That is just something else for that design. If you look at a different one,
We're free.
That's generator. This is for generator. See, it says GEN. So we're not putting a generator in. Generator. So what we're wanting to do is we need to bring the grid in, which is going to be over here. So when we look at this, if you want to come back over here. So when we look at this, what we have is we have this wire here is the grid, and this wire here is the grid. They're coming into the top.
Right here?
Yep.
Okay.
And then this stuff right here is what goes down and into here, up inside here,
Right.
where that is the grid.
Okay.
So we got to get the grid through that breaker all the way back down and up inside here, landed.
Okay.
Fault
I'll
48.
connect that up. Yep.
Turn this off. There you go. Okay. All right. I forgot how hard this was having class, trying to teach and run class at the same time and help you guys. It's hard.
Yeah.
I forgot to drive me nuts. He's tearing this thing apart, and I don't know if I want him to, but I let him. I don't see a battery doing. It's solid state. You might have to get in the manual and figure out how to do this password, and that don't just come off.
I was trying to, because all the kind of big use.
Yeah.
But actually, hang on, I can work this out. I'll put it back. I'll put it all back up on.
Okay, buddy. All right, I'm gonna leave these guys alone for a minute. I'm gonna try to charge my headphones and get you guys going a little bit. All right, virtual class. I don't have time for that. All right, so let's go ahead and put this away for a moment. And we're gonna go ahead and just oh, that's plugged in anyway. I'll turn that off. No, it's not wanting. There it goes. Okay. So now I'm just gonna stop sharing. Okay. Now what we have is class, right? So I'm gonna plug my headphones in over here, and I'm just gonna talk to you guys through the computer. These things are dead meat right now, dead battery, I mean. Okay, so we're going to jump into our class right here. And I think I got everybody. I'm gonna double check. That looks like it. Okay. So what we want to do is we're wanting to get into our PV sizing chapter 10. Okay, but in order to do that, we want to go into the textbook. So
I think I finally got her, and then she ain't coming in.
all right, so when we look at our class here, we have chapter 10. So we got all the way through grounding last class. What I want to do today is get us a good start on this chapter 10. And so by 3 o'clock, you guys will be well into it and not worrying about it too much. You do have, come back here and straighten you out. So I haven't done that yet. Let's go look at our syllabus. And then we can come down here and see that we are in week 6. Week 6 is technically installing PV systems, but as we know, we were getting into PV systems, sizing PV systems. We were working on that and NEC PV wiring. So we were doing NEC PV wiring last week, and we wrapped up with grounding. So we're really just starting chapter 10.
So it looks like we're behind, but we'll catch up quick. Okay, so we're gonna jump through this. Again, we don't have any new projects yet. We're gonna probably have just one more that makes sense, but it's gonna be more of a full design. So we'll talk a little bit about that today. You've already got your calculators and you got some of that stuff out of the way. So we'll just see what we can pull off. Best thing is, of course, coming to campus and wiring them up for real. So that's what these guys are working on behind us, and we'll talk about that as they go along. But to get started, we're going to want to jump into chapter 10. Now, some of you had mentioned to me that you don't know where to find stuff. And I put a link in here. It's in both week 5 and week 6. And it's a good link. If you go to this website, this has all kinds of pre-made systems, everything you could want. And so what you want to, do you want microinverters, DC optimizers, string inverters, ground mounts? Well, we're working mostly with string inverters. Okay, so you've got all these kits here that you can look through just to get you started. So let's say you want to do a 10,000 watt string inverter. Well, the whole kit is only $12,178. You get all that for $12,178. That's not bad. 20,000 watt system, that's a little bit more, but it's twice as much. Well, that's where you click on this and you can add the plan, set, and interconnection service. Remember how I taught you in class how to do interconnection agreements? That's part of this. That's something you can charge. See how much they're charging? So you'll have your plans and your interconnection agreement. They're charging $1,500. Now the plans do include generally a engineer's stamp or sign to do the actual class. So not class, to do the actual system. So if you don't have that in place, then you're going to have to pay for that. It's going to be at least $1,000 usually for an engineer to sign off on this stuff. So the $1,500 is pretty good, but you could make yourself $500 after you get your engineer stamp and your plans and all that together. But that costs extra, so you couldn't just buy this for $12,000 and put it in. You got to go to a inspector. You got to go to the electrical inspector. He's going to want to see these plans, and he's going to want to see that he or she is going to see that signed document from a real engineer saying that this is okay, because that guy's got to sign his life on a dotted line saying that he's approved of this, and if it fails, it's his fault. So that's just what the game is with some of these people, but they really just charge you $1,000 to tell you what you already know, which is really a sad truth. But you're gonna have to find someone to work with you on that. Okay, I've got my people. I call them up and send them some money, and they sign whatever I want. That's basically what you need to learn how to do, and that's just connections. Okay, you could go to any kind of engineering firm and they'll take a look at it. Civil engineering depends on what it is you're doing. Actually, if you're on top of a building and you're doing some weird solar system, building inspector is going to get nervous. He's going to want somebody who is an engineer who will sign on that, so he doesn't have to take responsibility. It's all about passing the buck around a little bit. But as long as you know what you're doing, you're really just passing that buck around to get your job done, and then you get paid, right? So this company likes to use these Sunny inverters. Sunny Boy inverters is what they call them. So you can click on it and you can find the different models. You can find your model if you want. They do have other inverters, but this is different sizes. So 5, 6, 7. What size of inverter is this? Well, you want to click on it and come down and try to see max PV power. That's a 12,320. Wow. It's made though for it's actually made for about 6,660 watts is what it's made for. And so that's really as far as you're going to get with some of this. They used to give you more stuff, but I see they're hiding some of this. But you should be able to get in there and find like the prints, the installation manual, all that for this inverter right here. One of the things that you can do also is do any inverter really, but if you want to go with this Go Green Solar, just pick a kit that you don't really know where to find all the stuff. That's why I've got this link in here. So they've even picked the solar panels for you, or you can pick them yourself, but you can see it doesn't really matter, but you got to add up the wattage, right? So this 310 watts, how many of them do you have? That's the size of your system, as we already know. But you have different ones. Look at those. That's $350 for 400 watts. Woo-wee. That's a lot of power. I'm going to have to get me some of these. Really. So they're getting up there. When we're hitting 355, 400 watt panels, I mean, that is some good stuff. That is ridiculously expensive there. $1.68 a watt, $1.17 a watt. That's what you want to look at. That right there, 89 cents a watt. Ooh, I even like this one. Got a 420 watt. So when you go with something like this, you're like, oh, cool. But what is the spec sheet on it? What is the actual? Okay, so when we look at the spec sheet, what we want to know is, well, they've got the different sizes here, right? But we know that each one of these 420 watt panels has a short circuit current of 10.74. Okay, so it's over 10 amps. And then the open circuit voltage, well, that's 48 volts. So we're at 41 when the system's running. That's where you're getting your 420 watts. But that's a lot. So if we put two of these together, that puts us at 48 volts times 2. We only can put two of these in series together. And if we parallel, well, two of them together makes 20 amps. So there's one of the issues that you're not really thinking about when it comes to putting in these big panels is your equipment can't even handle that kind of power, can it? That's the question you want to ask yourself. So it might be able to, it might not be able to. You want to be careful going with these non-traditional panels that are unusually large and expensive because nothing will work with them. So that's why you want to think about like, okay, maybe I don't really need a 420 watt. I might be better off with just a regular old 310 watt one. And these are really cheap. I mean, 310 watts for $227. You know, but do you want that? Now, when we look at this, we can see what our short circuit current is. It's still pretty high, 10 amps. And then our open circuit voltage is also pretty high. It's not quite as high as the other one, which is at 50. But see, so that's where it comes in, where you're needing to wire these in series or parallel to keep your voltages within your ranges and your current within your range of your equipment, such as your charge controller, which we know our charge controllers that we've been using, you only can bring in 150 volts DC, really 140, and then, 60 amps plus. So that's supposed to give you a little bit more of an idea of what it is that you're looking at. And how would I find some of these parts and pieces? You got a lot going for you in that website to help you look up name brands, look up different companies, different inverters, panels, on and on we go. So that's an introduction to that. I'm gonna try to put my headphones back on. I can hear better. Okay.
There we go. All right. It'll be switching over here soon. But what we want to do is take a look at chapter 10. Does anybody have any questions for me about anything before I get started on this? And then we're going to check on those other guys periodically. Okay. They're pretty busy over there, so we'll leave them alone. And we'll just jump into our chapter 10. So I think I need to stop share there. And we're going to want to do this right here. Okay, that'll work. Okay, so the thing about chapter 10, as we know, is it's just a lot of stuff in there. So I'm going to see how much of this I can get through today and try to point out to you all the areas that really matter. A lot of it, as I mentioned before, is just repeat information that you've already thought about or talked about in an earlier lesson. So we have some definitions of different things, you know, duty cycle, Energy Star. Energy Star is just a rating for appliances, as we know. How long does an electrical load operate? That's its duty cycle. So you have something that's on and runs for several hours. That's its duty cycle. The process of changing electrical loads in a building to another form of power, such as natural gas or propane, is load shifting. Phantom load, we know what that is. It's when we leave our stuff on, like our clocks or DVD players, things that are just always on with a little red light. It's a phantom load. Soiling all over our panels is a problem. Then we have the surge load, which we've talked about already with it being 250%. So let's move on to the next. There we go. Okay. So I'm going to speed read through this more or less and just tell you what's in it. So, you know, the book just starts talking about the different kinds of systems, you know, bimodal versus hybrid. So we know that there's several different types of systems that we can use. We've already mentioned a generator can help. There are complex sizing software. Yeah, I'm pretty sure you have to buy Homer, but I'm curious now. Let's take a look. I won't be able to get this on. This thing doesn't let you copy and paste. Let's just take a look to see if there is. Homer is something that we've looked at before. They got me all caught up in there, don't they? Well, how about that? Maybe we got it. Let's just see. I bet we go nowhere. Yep. You can't just do that because Homer costs money. So that link doesn't exist. And let's see, we don't want to do that. Whatever. All right. So let's get back into our textbook here. Make sure you can see that. I think you can. I don't know why I couldn't see it before. All right. So we know we've got different types of systems. Homer isn't a link that you can use anymore. I was just curious. You can get it, but it's pretty complicated. So, but the first thing we want to look at, as we've learned in the past, is to understand really what it is that we're sizing our system for. So we have to follow these steps. So these steps matter. So we need to determine the electrical load, determine the size of the battery bank, which we've already done in the past with our worksheet. Determine the size of the PV array, determine the size of the charge controller, and determine the size of the inverter. And finally, determine system wire size. We've actually practiced all of this already. We've done one where we've done a calculator on the load. We've done a battery bank chart. We've done the PV array. We've done a little bit of that anyway. Determining the size of the charge controller. We've done both the standalone charge controller and MPPT charge controller. And then we determined the size of the inverter for a standalone system where we had to pick the inverter and we also had to pick the actual surge current for that. And that's about where we stopped because then we were getting into the system wiring. And so we spent the last couple weeks going over that system wiring together, trying to understand what the NEC code is that's going on. What do we need to pay attention to? So the first thing is determining the load. So we don't need to spend a lot of time on this. We'll zip right through. So we know that we've got different loads in our house that will add up to a certain voltage. So I would recommend just taking a minute to look through this. If you don't know, voltage times current is how you get watts. I say pi, so P equals I times E, or intensity times electromotive force. P standing for power or watts. So we know that we've got different devices that their voltage multiplied by their current will get a wattage. And so these are good things to just look at, like that 42-inch plasma TV, 339 watts. I still have a 42-inch plasma TV. It's still rolling and working, believe it or not. So you've got a duty cycle. We already talked about these. Then we've already talked about the surge load, knowing that we need a 2.5 or 250% increase in the surge capacity of our inverter because, motors will pull an inrush current that is too high. Okay. So again, they're continuing to look at all the different watts that they use. So you add it all up, you find out what your monthly, you can look at your bill, all that stuff. This is just talking about making sure that you understand if you're going to build a tilted system, do we want to tilt to the north or to the south, more or less, So we generally match the actual wattage that we put on there. We can see that if we want it to be at, not wattage, the actual latitude. So we're like at 43 degrees around here. So you set the system at 43 degrees. But in the winter or in the summer, if you recall, we'll tilt it 15 degrees one way or the other because the sun is more directly above you in the summer. Your system is going to be more flat. All right. And in the winter, it's going to be at a sharper angle because the sun isn't in the sky as often. All right. If a building's electrical load is basically the same for each month, you use the month with the lowest insulation as the design month. If the building loads change significantly over the course of the year, you need to do a load analysis for each month, which we've talked about that a little bit. So you can get more detailed. You can use a chart like this, which is one thing that we have. And then you can build upon that and try to get it dialed in the best that you can. But honestly, the best thing to do is just look at your monthly bill from your electric company because they will determine how much you're really using and you've got a record of it. And so you can find that out pretty easy. And as long as your habits don't change too much, then you know that you're pretty close, especially if you're paying the same amount every month. That lets you know that you're using that amount or close to it. So once we determine what our building load is, right, as we've learned, we've got to move on from that. So we can see that you can use this worksheet to do all that. And if you're doing that in the worksheet, that's great. But what happens is once you get past that point, then you've got to continue to figure out exactly how close you are to the daily load. So this is what they come up with, right? So they added all their stuff up, and we've seen this. So they only have like an 11,489 watt daily load, which we know that is nothing. They've got a DC one here too, but we ignore that because we don't generally work with DC. Now, what's wonderful about being in chapter 10 again is we don't need to spend a lot of time on some of these sections. So we've already covered the batteries. So we know when we're dealing with batteries, we have to figure out all those things to put in our charts. We got to remember what our discharge is. So remember, when batteries are discharged more than 50%, unless they're lithium, right, their lifespan is diminished greatly. So now you'll need to use the battery specification to complete this part of the worksheet. I know that my electric car has, it's a 2014, so what is it, 8 years old, roughly? Can I do math? Yeah, something like that. Question, Josh?
Yeah, I'm ready to turn back on again.
You want to turn it back on? Did you find your password?
Nope, I know how to clear it.
You do know how to clear it, though? Good job. All right. We're going to fire this up for Josh. We're getting hot here. Turn this on, and we'll get back into our... So it's this one and this one. Batteries on. Batteries on. You've got fire in there. Okay. Then down here, we're going to fire everything up.
Well, it has nothing to do with that. Clear it out.
Okay. Be careful. If you don't know, ask, and we'll shut it off and figure it out. All right, so he's working on that over there. We'll go over there in a minute and check. But, you know, I was saying with my car that these things are still really good. And I don't remember, I really top them off. I don't run them to zero very often. I think that's why, even though they are lithium. And that's how lithium tend to work. But I'm pretty happy, you know, considering they've lasted that long and they powered my car endlessly. So we know what these worksheets are. There's different ones. So we've done that one like this before, where we find out our discharge limit, and that's the one that we worked with. So we don't need to learn how to do this. That was part of our project at the very beginning. You do have a lesson here where they're actually, and we haven't done enough of this. We've covered it, and I haven't really quizzed you on it, but you probably will have a little bit of this on your midterm. Your final is being able to wire up batteries in series or parallel, or panels in series or parallel, and understanding what the voltage might be. So in this case, we have 12 volt batteries, or 200 amp hour each. So we know that these are all wired together, so that's parallel. These are wired in series. So we see positive, negative, positive, negative. So this set and this set are in series. This set and this set are in series. Okay. And then we have this set and this set in parallel. Generally, what that means is you're at like a halfway point here. But what we would need to understand is how is that all added up. So they're saying that this is a 48 volt battery system. So that means that we've got a 12 volt row, 4 12 volt rows wired each one in series or something along those lines, because we'd have to have our voltage to add up. So we got 1, 2, 3, 4, 5, 6, 7, 8. That sounds like a lot. That's like 60 amps. So we need to take a real close look at this. Oh, Josh has a question for us, so let's go see. That should be 48 volts over there. Yes. Okay. Okay. But we're not making a big deal out of this right now. We spent a little more time in our SST 102 class on trying to practice doing parallel series calculation. Okay, so this is just a standalone PV system, array chart. We've done this, yeah, we've pretty much done this one. You can see the same concept going on here. So let's keep rolling. There's a lot of pages in this. Next would be the array sizing chart. So we've already done a little bit of that. I highly recommend reading through this. But when we're talking about standard array sizing worksheet, we did that already. So we had to put in our average amp hours per day, pump in all this information here, and then we're able to come up with how many number of modules are in the array. So we know how to do that. That's pretty easy. And when we look at this right here, again, you've got 26 modules. 1, 2, 3, 4. We got 26 of them, right? Of 2. So this is positive, negative, positive, negative. Let's see, then we get tricky. This goes negative all the way down here. Okay. And then what do we got here? We got positive, negative, positive, negative, negative. Really got to think this through. But they're telling us right now that with 13 strings of 2 connected modules, each of the strings is in parallel with each other. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That means 3 of these panels are going to one of these rows. And the other 3 are going to this one of these other rows. Okay? And so they add these all together, and we're able to determine what our voltage is and what our actual current might be. So we've already done this one too, a standalone PV system with a standard charge controller. So that was one worksheet that we did. This is the big one that we did that actually had the modules built into it. Okay, so it's really just a big version of this one right here. Okay. But that gives us a lot of the same information. But what the point of this is to find out the actual size of our charge controller. All right, let's see here. Then we have a standard charge controller worksheet right here, where we know when we're dealing with these, we have to multiply this value by 1.25 because we have the safety factor of things being on for more than 3 hours, right? And so then we also have to put in our safety factor. So we got that double 125 coming our way. All right. So mostly what this wording is just explaining these charts to you guys, which I think you understand mostly how these charts work. We're just wanting to touch on some of the details. So they're talking about the worksheet where we have a derating factor for battery inefficiency to 0.85. You know, we've got the array temperature losses to 0.88. So some of these are constants that you can use if you want to use those. They've got a calculator here. I don't think that works. I'm pretty sure that was all taken down a while ago. The derate factor is used to determine the DC to AC loss. So let's move on. Yeah, wait a minute here. Zoom in. I can't see what I'm doing. There we go. So that's the worksheet that we just did a while back, a big one. And you've got all the notes that go with the code. Okay. And we already read about this. This is where we're trying to get into the derate factors. So we're talking about the derate factors. The list of derate factors that need to be considered when sizing an MPPT and step-down type of charge controller in a standalone system. So the module nameplate, DC rating, you know, derating this stuff a little bit is going to be helpful for you when you're sizing the system, because you have things like the derate factors for AC wiring accounts for resistive losses in the wiring between the inverter and the connection to the AC load center. The derate for, what happened? Did you do that, Josh?
Yeah.
Okay. Yeah. Pause for a second, everybody. So
I think it stopped itself.
what we want to do is disconnect you from the grid. So I'm going to do that over there, and then you shouldn't have to deal with that again. Okay?
Okay.
So you got your solar coming in, and you got your batteries over there, but you got nowhere to send it. So I'm taking that away from you. So you were sending it, doing something over there, and you backfed the system.
Bye.
Yep. That's all right. Keep working on it though. You can't do that anymore. So you've got your solar system coming in. You should see your power somewhere
Yeah.
right there coming in. And then you've got your batteries that it's able to charge now. So you just can't take it to the grid yet. So,
Well, I know what I did.
all right.
I tried turning the inverter on, that's why.
Well, it shouldn't even. Try turning it.
Well, it's not gonna do it now, see. Yeah, see?
Out. What's it saying? Voltage low, air.
Because I tried manually turning on the inverter and it did not like that. That's why.
Well, it probably had more to do with these breakers not being right. So so one thing you might want to do is pull this off and just see where these wires go. I hate not being able to see. We try to label them so I know what's what, but that's still not very good. This one here messes with me because it's the same idea as that block over there. So maybe this needs to be off. Maybe that needs to be on. It's off right now, and that's off right now. So what is that? That's the question you want to ask
Don't know
yourself.
yet. I'm looking through this thing then.
Okay. All right, I'm coming back over here.
Wait, is this some kind of like putty?
Huh?
Is that like some kind of putty?
Putty?
Yeah. That white.
Yeah, that's just, I'm not sure what that is. I'm not, some kind of glue.
Well, I've never seen something like that.
I don't really know what that's doing. You don't have them, you do here. They're just stability, I think, to keep these things from breaking, mostly, kind of like a caulking. Okay, all right. So we've got these derating factors, guys, that you don't necessarily have to do. So when you come down here, we know that we've got to do the table 690 derating, but this is stuff to consider. So they're very close to 100%, but they're saying that all this stuff adds up, and it probably does. Soiling, unless you go out there and clean your panels all the time. Shading may be an issue. All that that's where they come up with their numbers. So those are things that we've already got built into our worksheet. And, you know, we can use them if we want, or we don't have to use them. Now, we're getting into the standard charge controller sizing. So when we're looking at the standard charge controller, we've already done that worksheet as well. That's where we just need to know the ISC and how many panels we want to put in parallel maybe, and then multiply it all out. This is really just giving us an idea. If we're going to have any modules in parallel in our system, then we're going to have to take that into consideration and how much that's going to increase our current. All right. So there they've actually done the worksheet. for you. So over the next several pages, we're just looking at all the stuff that we've done before. Okay, so we also did this worksheet here. We had the surge capacity. Okay, that's all standalone stuff, and we focus primarily on standalone because standalone is the hardest. You don't have any grid support. Okay, and then lastly, we were wanting to get into the wiring section. PV source circuit, PV output circuit wiring. So the total circuit ISC amps is multiplied by 125% and then multiplied again by 125% according to section 690.8 A2. Requires the first 125% adjustment because PV modules can deliver higher current than the ISC ratings for the 3 hours around solar. In other words, with solar panels being a solid state type circuit, then we have no other choice but to recognize the generation source, recognize their potential in the resistance is low, the temperature is low, cold outside, and we've got a very beautiful day, kind of like we have today, where our systems are really cooking. You know, we're hitting 4,000 or 5,000 watts on a 5,000 watt system right now. So they're doing good. We've also talked about the type of wire and copper. Okay. And we did this worksheet here, or started to. We haven't really got that far because this is where I stopped because I was getting too far ahead of us. So we're going to want to come back and revisit this most likely, and then also understand a little bit more on how to calculate a voltage drop. We'll see what time allows, but I think we get the idea when we're trying to multiply this stuff together. So we already took the long, hard road of looking through all those tables, tables 310, B16, those tables that had the wiring size. All that stuff's in actually chapter 9. We've already talked about the fact that we have 60-degree termination, 75-degree, 90-degree. All that has to be considered. We know that we go with 60 in most cases when we don't know what the terminations are. There is no need to use the 125% safety factor rules from section 690.8 when calculating conductor size based on voltage drop, because voltage drop depends only on the actual amount of current flowing on the conductor. Okay, so in other words, we still got to do a voltage drop calculation to make sure that we're within our 2% range. If we're not, then we've got to increase the size, just like if our current is not within the range of what the wires can handle, we'd have to increase the size. Even if our voltage drop is okay, you know, vice versa, if one is not okay, you're going to have to increase it. So voltage drop is what we're concerned with voltage, and then the actual current is what we're concerned with on the wire. That's what we size our breakers for. And so we've got to keep that within our equipment tolerance ranges. Okay, let's keep moving forward. This is really just a repeat of everything we have already talked about. Now you've got a larger, so you got a standalone PV system where you've got a wire sizing worksheet, battery bank to the inverter, or charge controller. So in order to do this worksheet, we got to understand what our inverter wattage rating is. So that could be what, 6,000. Divided by our inverter efficiency. So we could say 90% or higher if we want, or just leave it blank. But that'll give us our maximum inverter input for amps. Okay. So generally we're going to look at something more along those lines of around 95%. Maximum inverter input would come down here, and we would multiply that times our safety factor of 1.25. That's going to give us our inverter input circuit wiring size. Okay, but that's not taking into consideration all this other stuff. So we've got to ask ourselves, well, before we move to the next size of wire, in other words, this is going to tell us our amps, not our size of wire. We would need to do, is it copper, aluminum? Is it THH-N2? What is it? Lowest termination, 6 degrees, 70 degrees. What's its ambient temperature correction factor? That'd be outside, inside. Is it 100 degrees outside? Negative 40 degrees outside? What about our roof adder? We've already talked about that, where we need to add. And then more current carrying conductors, adjustment factor. So these are all percentages or things that we need to note in here. So now we take our maximum inverter input, divide it by our final ambient temperature correction factor. So we find that in our chart. Divide that by our more than current carrying conductor. Sometimes I'm not sure these should be multiplied or divide. So use your brain. I'm not always sure these are right. Generally, you're going to multiply them. But it just depends on what you're doing. So for dividing the amps, we're just going to go with what they say until we figure out if this chart is wrong. So we divide, and then we end up, after we've derated the wire, we end up with our actual ampacity that we need. So this first one isn't good enough because we've got to derate it with all this stuff here. The second one's better. Now we choose the larger of the wiring size amps of number 1 or wiring size amps of number 2, right? Got these little notes says 2-10. That means you need to come down here and read 10. This answer meets the requirements of, okay, whatever. So we could look that up if we wanted to. Now we got to look at our chart and find out which one of these is the one that we want. So whichever one is the larger. Then from our 310-15 table, we're going to pick the wire size. Use this wire size if it is the same size or larger than the wire size calculated based on voltage drop in section 7. So that means you're going to do your voltage drop. You're going to get K times I times L times 2. So our constant, seeing if it's aluminum or copper, times the current of the system, times the length we're going from point A, from the PV system to the inverter. We multiply it by 2 because we have a positive and a negative wire, so we're going there and back, and divide it by whatever our voltage drop would be. So in most cases, we're wanting 2% or lower, unless we're dealing with AC, which would be 3 to 5%. But if we do all this stuff here, you know, we got to know what the circuit voltage is, the maximum inverter input, one way. I like this chart a lot. I actually like it better than the other one we were working on. So I might switch us to this one. That one seems to have everything we've been learning on it. Pretty good. So that would be a good final project, maybe, to look forward to. So I'm just talking out loud, but we can plug all this information in. And we know we're going to get most of it from table 8. So let's move on here. Now this one has standalone PV system wiring sizing worksheet with battery bank to the DC load center or charge controller. So what we're trying to do is size the wiring. So this has whatever we want the DC load to be, if it's got a wattage. The system voltage is the total system amp. So that's just going to give you, you know, so are we feeding a DC load wattage? Not necessarily, unless you got a DC system. Okay. So we simply need to divide whatever wattage we're using. So it could be AC or DC. So you could say it's 12,000 watts divided by this voltage, and you're going to get your DC amps just as well. Determine the type of wire, insulation, the terminations, what the ambient temperature correction factor should be. Are we on the roof? Do we have more than 3 current carrying conductors? Then we're able to determine the circuit wiring size and amps. So that's all the way up here. We bring that back down here. We throw in all our numbers. Now we've got our ampacity. We bring it down here. We want to make sure it's within the range. And again, we still got to go back to our voltage drop. So you can see this really didn't give us a whole lot of detail on how many batteries we need or anything. So, you know, this is just trying to get you the wire size. So the wire size is really what you're concerned about. We pretty much deal with 4-aught wire the whole way. So battery bank to the DC load center, that's going to be 4-aught. If you're coming from this school, this program, it should be 4-aught. You try to put like number 2 on there, you're asking for it. That's all there is to it. So you really don't even need to do this. Use 4-aught wire. Let's take a look, since we're talking about it. Let's just review what 4-aught wire looks like. So I'm going to look this up here. Go for a little quick walk. I'm going to stop sharing this. And then I'm going to share to my phone. And should be connected here soon. There we go. Okay, so I'm going to walk over here and we're going to look at this cable on the ground right here. So what we do sometimes is we'll make cables. This is welding cable right here. This is 4-aught. You can see it right there. It says 4-aught. And what we'll do is cut these, crimp these, and put heat shrink on them. So there's what the wire looks like after you trimmed it. But you want this stuff to be soft. See how soft that is? I made the mistake of not buying the right cable. So welding cable, 4-aught welding cable is a secret. This stuff is gold. Okay? And then you just get a big thing of heat shrink. And you start crimping with your hand crimper. Get 4-aught lugs. These right here. Press these on. Cut some heat shrink. And then use a hair dryer, basically. Heat it up. And you'll have that. So when we look at these battery systems, we can see that all these cables are made with this 4-aught wire all the way through. And that's the way you're going to see all of our systems. So we can see that goes all the way through, and that comes all the way in here. And then when we look at these systems over here, we're looking at wire size, right? All these big fat wires are 4-aught. They're coming in right there to the bottom of your inverter. Those are supposed to be 4-aught almost every time. Okay? That's the way you want to do it. So we got these ugly batteries in here. They still got 4-aught on there, but the insulation is too thick. Stiff. Those are not solid cables, but it's just not very good stuff. So we've learned our lesson there and went with strictly welding cable. You guys have any questions on that? I'm going to go ahead and hit stop share. Excuse me. Okay. So next thing we want to do is get back into our textbook and keep powering through this chapter 10. So there's really nothing here that we haven't already looked at so far, right? So far, we're handling it just fine. We've seen it before. We've done it before. So they start to get into inverter to AC load size wiring. I really wish I could get rid of those little highlight things. I don't know how they get in there. But this whole thing is standalone PV wire worksheet, inverter to load center. So we get our inverter rating, what our inverter output is, and then we get our inverter continuous output circuit current. Okay, so again, I'm just taking wattage divided by amps. That gives you volts. All right. What is it specifically? There you go. Inverter continuous output current times 1.25, which is going to equal the inverter wire sizing amps number 1. Well, we've already talked about this, so we've got to run across with all of our correction factors. Then we're going to move down to inverter continuous output current here. Final ambient temperature correction factor from up here, and this from up here. And so we end up again where we've been coming. We've got a wire size number 1, wire size number 2. We choose the larger of the two numbers, 1 or 2, and then we go to our 3, 10, 15, B16 and find out, depending on what our lowest terminations are, which they'd be under the 60-degree column most likely, and whatever the amps are of the larger. So this is like 60 amps on number 2, and this is 40 on number 1. And we're going to go with number 2, and we're going to try to find a wire that will go with 310. But we've already put in all our derating right here. So we almost always are going to go with this number 2. That's all I'm going to say. If you don't have any of these issues here, you might go with number 1. But you're going to have all these issues. So then we do the same thing we did before, where we're just trying to do our voltage drop to find the size of our voltage drop to make sure that we are able to determine which one of these wires needs to be the big one. So we do all this stuff to eliminate us making a wire too small. Okay. So that there doesn't really do anything with a standalone PV system wiring worksheet. So what's on this one? Well, this one is a wiring sizing worksheet for your solar system. Well, if I take all my panels and hook them together, whether it's positive or negative, I just hooked let's say I hooked 20 panels together. They could be on the ground. I'm just clicking the positive and the negative clicks together. At some point, we're going to have a certain amount of current and a certain amount of voltage coming out of these panels. When we have that much current, that much voltage coming out of the panel, then we have to determine what size of wire we're going to use. So generally, they all have solar wire on them, but that is not the system sizing wire. So we want to determine, when we've combined all of these panels together, what is the actual total current, what is the actual total voltage coming from the system, specifically if it was wired in series or parallel. So once we've determined that, then we can see that we can pop in all of this information like we did before, and then we're going to end up with, so there's this one right here. So we've got a ISC of 8.52 on our panel, times we want to put 13 in parallel, so we get a total of 111 amps. We multiply that twice, remember, and then we got 173 amps. Well, now once
I
we
don't think you're
derate
sharing
the
your
wire,
screen.
what's that? You can't see it?
Yeah, I can't see it.
I'm not sharing. Thank you. It says I'm sharing. Just reshare it. There it goes. You see it now, Brian?
Yeah, now I can see it.
Okay. All right. So it must not have been sharing. All right. Thank you. So this is all we're looking at. So we have our PV module of 8.52. Multiply that by our, however we want, right? How many we want in parallel. We can change that number. That's one of the things we can choose. We get our total circuit. There you go. We're at 173. Then we do our derating factors. Okay. We've learned how to do that already. We're still a little rusty at it, but we know what we're talking about, right? They picked that off the chart. Then they run that through here, 111, okay? And then they're going to multiply that times 1.25. And then they're going to take that times 0.71. And then they're going to divide that by, well, do you have that or not? So they don't. And what you're just going to find every time, guys, is if you're going to mess with any of these correction factors, which you will, you're always going to be bigger on number 2. because that's where you should be. I mean, 195 versus 173 is quite a bit of amps. It really is. So we know we want to go with 195. If we go look over at our wire sizing chart, 195 puts us at 3/0. Well, then we go over here and we have a 48 volt. We know that we're at 111 amps total circuit ISC. Okay, that's just what the ISC is. It's not the wire size with all our correction factors. We know we're going how far? Well, they tell us 60. Okay, so that's going to have to go here, and that's going to be multiplied by 2. We're going to limit our voltage drop to 2%. We add that up and do the math, we're going to end up seeing that it's 4/0. So we can't use 3/0. 3/0 is too small, and you'll have a larger than 2% voltage drop with 3/0. So what we need to do is simply go with 4/0 almost every time. It's right there in front of our face too. That's another reason why we just go with 4/0 on batteries. But we're talking about wire sizing of the actual PV source circuit and PV output circuit. That is a huge wire to run 60 feet. You realize that, right? That is insanely. I don't do that, and I would never do that. So what you would need to do is not wire it up this way, really. So we have modules with about 8, okay? And we don't have nearly as many wired in parallel, okay? But it complicates the way it works. So we got to go 3 in series, 3 in parallel, 2 per row, then 4 rows of parallel. So everybody's like, well, how do you do that? How you do that stuff is you use your brain. You have to think about what would work best. And the easiest way is just meet it in the middle. So if you got 30 panels, build the system to be half in series, half in parallel. You do that every time, that's probably going to be your best anyway. So don't even stress it too much. Just shoot for half and half. So if you've got a 26 panel system, then 13 of them are going to be in parallel, if you can do that. Okay? But you'll start to run into some of these issues here where you get a system that's ridiculously, the wire is just way too big. So we have to ask ourselves really what's going on here, because we don't really know what the wattage is on these panels. I don't think. We could figure it out. They're not that big. But no, I don't like this system. I think we could do better than that. In other words, we've got a very nice solar system running right now that goes way farther than 60 feet. And it's a big system, and we're only using number 6. Now, one of the reasons we're getting away with that is a concept that they're not really talking to you about. So I'm going to go back to our camera here. Hopefully this will fire right back up. I hate that thing. Share phone. Go for it. Hey, that zoomed right back in there, didn't it? Okay, so when we look at this, we're looking at the fact that we have these wires coming in from outside right here. And there's a bunch of them, okay, because we got parallel conductors. We don't want to run 3/0. 3/0 is just one big wire. What we can do is run 3/0 in multiple sizes of wire that's smaller. So we've got basically 4 negatives and 4 positives coming into the building right here. Okay? And so what that does is it just allows us to have a smaller wire. So you can wire these systems up many different ways, but they're not all going to be the same, more or less. So you could do it 4/0. You could do it not 4/0, 3/0. When we're talking about batteries, that's the 4/0 deal. The systems don't necessarily need to be 4/0 at all. So we want to make sure that they are close, but understand that even though 4/0 is a very large wire, you can separate the system out into rows. So literally, if you've got 26 panels, or let's just say 24, you could divide that into 6 rows or 4 rows of 6, however you want to do it. And then each row is coming in with its own current and its own voltage. And that allows you to bring a smaller wire from that row into that pipe into the building. If you want to combine everything outside and bring in one ginormous 3/0 wire, I don't know. I really haven't found that to be cheap. It's much cheaper to use smaller wire. Big wires, you'll find out when you look around. So that's one thing that's going on that we're doing. Come on, there we go. Okay. Let's check on, how you guys doing over here? You have any questions for me?
I don't want to touch the thing anymore in case I press the wrong button.
So put her back then, if you're done with it, unless you want me to come over and take a look.
Yeah, but, I mean, I got a password off of it, so it's no longer password protected.
That's good.
That's good.
That's good. We're only got about an hour left here probably. So that is a huge one. I would say you accomplished a very good goal, because what we can see is that you are charging. You're on a float charge, and you're doing 1.16 watts back into the grid.
So what's back to the grid?
Yep, you've got,
Didn't turn off the grid though?
you're still off on the grid,
Yeah.
but you're charging your battery.
So,
Now, we can connect back to the grid, but I need to understand what these are doing here.
I'm trying to,
that one won't let
I
me.
can take the panel off.
You did?
I can.
I would. Do that before then. Take a look inside there. Just because I think we'll let everybody go in class, and then we'll try to finish this up. If we can't do anything, we'll just,
I'm trying to remember how to dump the batteries out, some batteries I can,
so that would just be if you put them into the grid.
yeah, I'm trying to dump the batteries into the grid.
I don't know why we got a feedback at all. I know you went and did invert, but I would have done that too.
I turn the inverter on manually.
But that's what I would have done. And I don't know why it would have done that. It shouldn't have done that. It should have just covered these loads.
I'll tell you what fucking happened. Backseat air.
It was a backfeed. You can hear it. When it does that, zzz, that is a backfeed sound.
Well, this
You know.
just happened. That's not a good sound.
It just happened now?
This one just happened.
Well, yeah, but that's today at 1:48.
Yeah.
That was an hour ago.
Oh, was it?
Yeah,
Oh.
it's like 2:30.
Yeah.
That was the one.
Yeah.
And that's what those sound like. You know, that's these little toroid transformers in here and relays going all wacky. They're making that humming noise right there.
What did the backseat sound like?
Let me get our camera on so we're not leaving everybody out.
What happened, like, the buzzing sound?
That buzzing sound,
That happened. That happened.
yep. Yeah, this sound right here is good. You hear this humming? That's just electrical. All transformers sound like that, because that's the magnetism in them. So there's just this vibrating magnetism that we know is there. We can hear it. We could even feel it, but we really can't see it unless it turns into a bolt of lightning, right?
I just want to point out, this is doing pretty well right now.
Yep. So we are at 3.7. So you also can look at that over here, Cameron, on this system, and you can get a little more detailed information. So you just hit exit here. You can see that this system, H52, yeah, this one's off. So we're slowly using a little bit of the battery. We have a 260 watt load on that system there.
Yeah.
And then over here, this is inverter 1. So we are, we've got what's it say?
3?
3.6? So it's a combination of these two numbers here.
Okay.
See that? I don't know.
Now we're really confused about that. So with that number right there, 3.7. So
Uh-huh.
does that mean like if it was left at that exact same rate for an hour, it would have gained 3.7 kilowatts?
Yes.
Okay.
Yep. So if we were at 3,700 watts for 1 hour, that's how many watts we just had.
Okay.
But it's over 1 hour. So really a meter just spins. So as the watts decrease, the meter slows down. So like 1 watt, it doesn't even move. 3,000 watts is spinning faster. And so the dial keeps changing, telling you how many watts you've used. So that's how that basically works. So it's constantly changing.
So say
So it's an average.
say hypothetically, you turned all unnecessary power to on, like all the lights in this building and whatnot.
Uh-huh.
You gained all a bunch of power in one day.
Uh-huh.
How long, like, and like say we came back the next day, like how long will that power last? Like how much time or just length? Basically,
It's just how many amps
yeah,
you pull.
just-
So if you pull 1 amp, then you're gonna pull how many amps you have. So if you've got, you say you take that power, so that's 3,700 watts.
Yeah, it's like how long would that last?
Okay, well that's at 240 volts. So if we divide 3,700 by 240, that's gonna tell you how many amps you have. Yeah, I don't know off the top of my head. Well, 20 is gonna be 4,000.
About 15 amps.
Yeah, about 15 amps. So, you know, that would be for 1 hour. So that means 3,700 watts would supply 15 amps of power. So 15 amps of power could be at 120 instead of 240. So most of our outlets around the building are 120. So they can handle even more.
Yeah.
So in other words, that would go twice as long because you're only using half the voltage.
Yeah.
But if you're doing 240, the full voltage, which is what this is coming in, you know, then that is going to be just straight up 15 amps. So when we look at these batteries, we see these batteries are rated at 200 amp hour. That means this battery at 100% discharge can give you 200 amps per hour. So if we're getting only 15 amps from that, we'd have to charge this several hours, right, to get the ampacity in here. Now this is a 48 volt system, but we're only at 200 amp hour because we're wired in series. So most people in their homes only pull about 1,000 watts an hour, 1,000 to 2,000 watts an hour. So we just did the math on that. So we're talking like 10 to 20 amps.
So basically, if I were at home right now, I'd basically only be able to run like everything in my house for like an hour or two before everything would get out. Basically.
Oh, probably not even do that.
Really?
Because what happens is that's just the humming.
Oh, it's not
That's like the lights on, and so like right now when we look at this inverter, come over here. This will help you understand.
It's probably not 100% efficient in the way it uses the power, right? It's gonna be just natural loss. at this
Right.
point.
So we've got these lights right here. You can't really see it, guys, but it says 847. So that means these lights right here in this room, they're basically pulling all of that. So if I turn that off, that'll go away. But right now, you can see that 1,000 watts is just going to lights.
Can I turn off a light switch and see if it changes?
You can go over there and turn the switch off, and we'll watch it change. I don't think they can see it, but
Don't worry about it.
Yeah.
Good. I got a flashlight here.
there you go. Now, what's it say?
Oh, dang, 130.
130. Yep.
We just
So,
reduced
yeah.
700 watts of load.
yep.
by turning
So
the
you
light.
can see that in your home, you could be just using a lot of that power but you don't need the lights, right?
Yeah, so is this like our net gain of what amps?
We're charging our batteries and using the power. So the solar outside has got enough to run these loads, which they're not the same anymore. And then all the extra, what's that say, 35?
Yeah.
All the extra now is just going back in the batteries
Gotcha. So,
or the
what's up
grid.
with this one? This one doesn't really seem like it's doing much.
That's because that's the one that you have off.
Oh, okay.
Yeah.
Gotcha.
I'll turn our lights back on. That's the one you're working on. So yes. So in that case, yeah, 10,000 watts an hour is what this thing's supposed to be able to do.
10,000 watts an hour, you said?
Both of them,
Okay.
5 each.
Oh,
And it's at about 80 plus 90% capacity almost.
what's 6,000 watts?
Yeah, but you only got 5,000 watts of solar coming in.
Was that like what it maxes out at though?
Yeah, 6,000 watts is the size of the inverter.
Okay. So like, meaning like it'll store that much, or is it like
It doesn't store anything,
okay, okay.
but it inverts that.
Okay, so it basically, that number will never go above 6, is what you're saying.
It'll never go above 5, but
Oh.
yeah, it won't go above 6. It will go above 6 because you have surge capacity. Right here, you got to read this stuff here.
But it won't be too high about it. I'm not understanding.
Well, surge capacity only lasts for about 10 seconds. So you have to read through, I can't see it with my glasses. Good old man eyes. But if you run down this list, let's see, let's look for surge. Let's see a surge. There we go. AC output surge, 15 seconds. This will do 12,000 watts
Mhm.
for 16 seconds, 15 seconds. That's not bad. That's an awesome surge capacity. So that means anything in the house that turns on, like your furnace,
Yeah.
is going to pull a lot of power right away. And that's going to want to keep this thing from turning on. Now, we can test that. You guys are into testing mode right now. So we have our heater on this load. So we can turn on our heater and we watch this load increase quite a bit, or our air conditioner. But I'll just come over, watch that number there. I'm going to come over here. Crank the heat. See it? Yep. Did it turn up? Did you gain a little?
We'll see what happens.
It didn't really do anything.
Well, maybe it hasn't just kicked in yet.
Yeah, I should have done a little more than that. Well, if we do the AC, then I'm going to have to go outside and fix it. I don't think they've done that right yet. There you go. How about that? Now you're getting some power? Yeah, that blower fan's only going to be about 200.
Yeah, it jumped up and then went.
Well, then look at this here. We talked about the solar. That's 904.
Back to 1,000?
Yep, it's almost maxed out. So it's at 90% sun availability to the sensor outside, but
Wait.
that's on the tower out back.
Wait, how do you know it's 90%?
Well, it's out of 1,000.
Oh, okay.
Yeah, that's your watts per square meter.
Alright.
Okay? Yeah, this really isn't doing anything. But you get the idea that you're going to have these large loads coming in.
So how many panels are feeding into that one inverter?
18 280 watt panels. So 2 rows. 1 row here, 1 row here. Yeah, you're in amazement now, aren't you? Starting to put it together.
I want to go outside and look at all.
Well, go right ahead. You want to go out and take a look? Yeah, that's part of this. Okay, let me get back to you guys. Yeah, we're not going to be doing this a whole lot longer, just so you know. Let me share my screen again. Okay. So hopefully you guys that can't be here and haven't got to see any of this stuff, these guys are asking good questions and you can see they're answering some of the same things you may be curious about. Okay. Let's move on. Just turn that thing. Why don't you want it to work? Okay. There we go. So this is the wiring sheet. So it's more or less the same thing. We've already talked about this one. I don't know why we're looking at it again. This one is where they've actually put in the numbers. So when you start to get into some of this stuff, you start to see that they pop in the different numbers. So you got your inverter rating, and right across you go. So those are good examples to look at. And all these large paragraphs are just explaining step by step what they're putting in those boxes. Then we get into this sizing a grid tie PV system. The grid tie system is really not a big problem because we've got the grid, right? So we can size this thing wrong when we're dealing with grid tie. This is standalone again. They're just throwing a couple examples. So grid tie is really just if you want to put in a small system that doesn't power all of your loads, then you're in trouble. How you guys doing over here? You just rolling along? You got a question?
No.
Just rolling along. Very good. Okay. Just checking. I don't leave you hanging by yourself. So we've got this grid tie load sheet that we can do. They've also got a really short version of it, which seems to be the way to do it, you know. But I'll be honest, I don't really care much about this worksheet because it's just based on whatever size of system you can afford. All of us, if we could afford a bigger solar system to run all our loads, we would. But that's what a standalone system is a system that is designed to run a very specific set of loads. If we don't know what that is, or we can't afford one, then we should go with a grid tie system if we can, and which is what most people are going to do because it's what makes the most sense. Now that we know that we want a grid tie system, then it really isn't about sizing the array as much as understanding that you still have to create or do a calculation that involves the NEC code and the different limitations that you get when you're dealing with wire size, right? So grid tie array, let's see what they got here. So when we're looking at a grid tie array, what we're seeing is we need to answer a lot of same questions. How many hours of sun do we get per day? How big of a system is that we can afford? What is our inverter efficiency? Then they throw in their constant of 0.88 array temperature losses divided by system losses, which is fine. All that's going to do is make your system a little bit better and less likely to be undersized. Once we find out what it is, in the kilowatts, then we can determine by following along here how many, we're talking about 1,000 watts per kilowatt. Now we can find out how many actual modules that we need. So it's a pretty easy worksheet there. So you can see the example they have. So we want a 12,000 watt system. That's pretty good, 5.3. Inverter efficiency 0.9, 0.88, 0.8. So we end up with the PV array is 3,360 watts. So we take 3,360 watts times that, we're going to get 3,360 watts, and we got to divide it by, well, our inverter, or our home system, is 200, well, that's the panel right there. So our panel, we pick our panel, okay, for our home system. So it could be one that's 310, or one that's 400, or one that's 240. And then we quickly determine that we only need 14 modules. If we can figure out what those modules are, say we can put 14 in here, now what we can do is determine what our inverter needs to be. So again, our PV module rating, 14 times 240 is going to give us a number. So let's see if we got let's go with this worksheet here. So we figured out we wanted 14 on the previous worksheet. Then we know that our panels that we chose are 240 watts each, and we get our 3,360. Now we're trying to find our inverter size, right? So we move that down and we divide that by the chosen output power rating. So this inverter can do 3,900. That tells us we need just one. Well, that's pretty easy math, right? Number of modules 14 divided by number of inverters 14. Very easy math here. It just comes into play when we have an inverter that's smaller than this one. Okay, then our actual, so we're going to end up with having to have two, which seems to be pretty straightforward. All right. So they also have to do the same type of worksheet for a grid-tied PV system. We still have to determine our wire size. So yes, we have the same number of things to consider to where we come up with our total ISC. We got to take it times 1.25, 1.25 twice. And then we got to run all the way across here, okay, where we have a better understanding of all those derating factors, bring it back in and finish it off. So let's go to that sheet where they did that. So same module, 8.52, run that all the way across. We got 13.3. We know the second one is always going to be bigger because we're going to derate it. So we're always going to go with the second one anyway. So now that we got the actual number 2, 14 amps is what that is. Okay, and don't be confused. 14 does not equal 14. So 14 amps is not very much power. 14 gauge wire would handle that. I'd never go anything less than 12. That's not what I would do. But then you find out that they do their voltage drop. They got to do 12 anyway. So you can see that most of the time, your voltage drop is going to be your determining factor. Although I lean less likely on the voltage drop and more on the wire size, to be honest, because even though I've calculated voltage drops where I had to increase the wire, I never saw it. Not enough to make a difference. Because a lot of times you got like 49 volts, or you got like our 208 today when we looked at it, we are like 212. You still can lose maybe 10 volts and still be within your range, because they're assuming that that transformer, that grid is actually bringing you 240 or 48 or whatever it is that you're working with. But that's the proper way to do it. So we know we'd want to go with 12 gauge. And I probably would just upsize it anyway, because I just don't like 14. That's speaker wire. That's the size of wire you put between your speakers in your sound system. I don't want power on it, not my solar power on it all the time. So that is teeny wire, which would save you lots of money, but it would cost you in the long run, if you ask me. So now they're just going to go back through the same concept, everything that we did before. And so let's take a look at what they did for their wiring size for their inverters. So they have 3,900 watts, right? We've got our inverter output circuit voltage. Well, we're dealing with a house. We're going to have 120, 240, right? And then when we're dealing with our inverter continuous output circuit current, we got 16.25. Okay, so now we know we got number one. Well, we oddly run this through this second one, and we don't really have any of these correction factors, because they're only taking, you know, nothing basically here to multiply. That's why they're less. That's why they end up with 16.25. What?
We're looking at the turbine. It's actually spinning so fast out there, but like the camera can't pick up how fast it's spinning.
Oh, yeah. Trickster. Well, that's because it's at a different frequency.
Yeah, it's not picking up how fast because it's kind of right.
So it's going.
It's going.
Before we go, we just gotta take what's in the batteries.
What do you want to do?
You want the disconnect switch to spin. Yeah, so it's been free, like the big one?
Yeah.
Yeah.
Just go out there and pull a disconnect
Where's the disconnect?
outside. Just pull it. But it's going to take 5 minutes. Then put it up. It's the one right in front of it. Yeah, it won't hurt. You got a couple disconnects out there. This one has a lever. You're just gonna pull it. As soon as you pull it, you see the turbine just stop on the dime because it's gonna put electrical magnetic torque, dynamic braking. That's a counter torque. So the magnetism is gonna break it. There is no brake in that thing. It's all electrical. Kind of amazing. Direct drive is non-gearbox. That is a direct drive technically.
Say drivetrain for some reason. I don't know.
Well, that's part of it. Direct drive is part of a drivetrain. Drivetrain is where we have a gearbox in a generator.
I knew it.
Yeah. So now you've got a system that's direct drive. We eliminate the gearbox. It's still drivetrain.
Yeah.
Okay. I'm glad they're having fun. Cool. You guys are over here like wiring like you run a company or something. I mean, you're just going to town. That's good. Good. It's like, he's got this. I need to pay him $500 or something. Right? Thanks for your work today, sir. So those guys are doing well. So we noticed that we're going to go back to this here. We noticed that we're going to go with the actual larger one here only because we didn't put any of these correction factors in. That's really what the difference is between these two numbers. Okay? Now we can see that we need 10 gauge, and oddly, when we do the voltage drop this time, we're at 14. Well, you know that we have this 1.25 only in here once. Okay, because we're not talking about the PV array wires. We're talking about the actual AC inverter wires here. So there's a little bit on that you need to consider. Oh, look, we got to the end of that chapter just like that. Can you believe that? We got through this whole thing together. Woohoo! And I'll be honest, that's all there is to this. You guys don't need to read through all this stuff here. We've already done most of this work. You do have some new charts on here, in here, that are making this a little more complicated, but, you know, it's still the same thing. So I think I am done with this. And that means next class, we're going to be able to go ahead and get started on installing the PV system. So we'll get started on it, talk about it. I'm going to probably take one more of these worksheets here, and it's probably that big one. That's standalone. Okay. One of these two we'll probably end up doing. But mostly what we want to do is just try to design a system. And so let me see what we already have, see which one of these worksheets, if not one or two, is going to be the best thing for you to just do right here at the end. And then you'll really know how to do a system properly and know what you're doing and why you're doing what you're doing for the most part. If you don't know, then what you need to do is get into chapter 9 and chapter 10 and start reading some more, because there's just little bits and pieces there that you're just going to have to go over, guys, and over and over until it all starts to click. I remember I had the hardest time remembering what short circuit current was, ISC versus the VMT or the IMT, and I couldn't keep that straight for nothing until I just went over it enough and it started to stay in my head. So I know there's a lot of these things that I'm throwing at you that feel like they're flying right past you, but that's where you go back over this stuff after we had our lecture, and then we talk about it more in your daily life, in your career, in the classroom, and then all of a sudden everything's going to start coming together. So we'll do that. To wrap up our final project is what we're going to do, and then you'll feel good about it too. We might do it in a more of a presentation form too. But that is my plan for you guys, and I know you can pull it off because you've done most of those sizing charts already. You could even use the ones that you had. I just want you to feel like you can do this, or at least much better at it than you did when you first started. I think everybody was having a really good time reading schematics today. I think that was good for everybody to see that you know how to do that. That thing turned on by itself. Huh. Okay. But other than that, that's all I have for this class. Now, was there questions that you guys have on your homework or anything like that? All you really need to do is finish up. So we look at assignment 5 for now. Sure, I'm looking at this right. Quiz statistics. You know, you guys are still working on 5. So I'd say you finish up 5 and try to finish up 6 this week would be our goal. Okay? Get your homeworks done there. Yep. In assignment 6. And then we're going to have our final pretest over these 2 chapters. So it'll be about 30, 35 questions. Not real big, maybe 25. Mostly over your homework questions. Okay? And then we'll have this final project put in there. That will just take everything that we've learned and let you guys try to pick a system, pick the panels, pick all the stuff, and put it in the chart. So I want to make sure that's not too overwhelming. So we're not ready for that, but that's the plan. But to get ready for that, get all your homework done, make sure you've taken all your exams, get that out of the way, and then I can get that all graded. Then we're going to do chapter 11, chapter 12. That's it. So all we have left is chapter 12 after this one next week. So this one's open right now, and on Wednesday, we'll go over this one together. But you can get started on it right now. And then next week, we'll just have our final chapter, week 7, over that, and then we got to get ready to take tests. Okay, we've got the ETA exam coming that we need to practice for, and we got to have those conversations. So we've got about 2 or 3 weeks left, and I'm going to get your practice test in there. It's just going to be keep going over it, keep going over it, keep going over it until you feel like you've learned it by the back of your hand, and then go take the test. Okay, that's what we're going to do. So get your mind ready for that. All that's coming to a head real quick, and then it's over. It's summer. So does anybody have any questions about schooling or classes right now, or you need help? One thing you can do is sign up for an appointment with me. So if you're not able to do this by yourself, which most of you aren't, I try to give you that much credit to try to work through that stuff. Then what we need to do is start having you guys sign up on appointments in the afternoon, like a Tuesday or a Thursday. You can still have an appointment and not even visit with me, to be honest, because all that does is set time aside for me to know that you need me to help you pick your classes. Then once I do that, I'll just spend that 30 minutes by myself doing that for you. But if you've already done it, I don't want to do it and then do it again and again for everybody else, right? So I can't sign up your courses for you. You have to do that. But all I can do is recommend what you need, which I know you need me to help you with that. So if you don't know when you want to do that, just remember, we only got about 3 weeks left, and then I'm off the radar, and I'm on summer break. And so it'll be harder to get signed up without me for sure. And so we want to try to get that knocked out here, right here at the end. Okay? Does anybody have any questions for me? I'll let you go see. I got somebody asking.
How many cert exams are we doing? The ETA and the CWED, is that right?
Yeah, you can do, you want to do them all if you can. So you've got the OSHA 10, which honestly isn't, if you're like, that's too much, I can't handle the OSHA 10. That's only a $20 test, I think, and you can do that on your own. But you've already paid $20, you might as well give it a whirl, but you're going to need to study for that, which we did that in our Energy 100. We went over all that OSHA stuff. You just didn't realize it. So we've got that one, okay? So that one will be an online test that I don't know really if you have to be here or not. I don't No, I think you can just take that at home on your own time. So that one's not too big of a deal. So we'll get that one. The CWED test is from that class. So the CWED test, we got a practice exam on that one too. That's in that course. You guys don't know if you have access to that or not. I can fix that, but I want to drop them in for you. So you have the CWED one, which we can do that one online, or you can do a bubble sheet here, which I recommend the bubble sheet just to get it over with. Or I'll just put everybody online and we'll pay for it that way. And then we have the 2 ETA one, which you can do. Actually, I'm sorry, the CWED has to be done online, but you can do that on campus here at CPAC, the Craig Porter. So you just come to school and do all your tests in one day is what I would suggest. Or we can just start knocking them out. So some of them we can do at home with you guys. The CWED one you can, the ETA ones you can too, but then you're on your own with some proctor watching you on the screen or a computer watching you, and you can't like walk away, go to the bathroom, or do anything. If you just come here and do them on bubble sheets with me, you're going to have a lot easier time, a lot less stressful, and I'm there to help you, okay? And we'll just get them done. And then I'll send them all off, and then they'll send us your certification. I just got to send them a check. So CWED, OSHA, then you've got the ETA Wind Installer 1, and you got the ETA Solar Installer 1, which goes with this class. Again, I'm going to have these tests that are basically similar in almost every way to your real test. Just maybe a spin on the question for you to practice. That way you know what to expect. And then anything that we need to talk about, we'll be able to talk about that ahead of time. Just get your mind ready for that. Good question.
Can we do the testing during like Monday or Wednesday class or lab time on campus?
Exactly. Yep. That's where I was like the bubble sheet. I've already got those. So if you can make it, and we didn't say that we wanted you to take the test this day, so we haven't paid for anything. But if you just come in and I go, here's the bubble sheet, fill it out, give it back to me, you're done. All I have to do is mail it to them with my credit card number, and you're done with that. The ETAs, they're super easy that way. That's what I would do for the ETAs, is just come in and do the bubble sheet. If you cannot make it to do the bubble sheet, then you get and then you're going to be stuck at home, period. Like you got to drive 4 hours. We can set you guys up to do the test online. So you could do it at home on a certain time, but you need to communicate to me whether or not you're really going to do that, or I'm just throwing money to the wind. And I would rather you do it in a way that works best for you. But if that's the way it is, we got to take it at home, we can do that. I just need to know who wants to do that when you're ready. Or you come into class on campus here during those class times and take those tests and get them knocked out that way too. So you could do it all here on campus. If you show up, we'll just start testing you. Okay, the CWED test, I need to call ahead. I can't do bubble sheets on those. So CWED, I feel like I'm just going to pick a date, like May 7th or something. That's not the date, but pick a date, and I'm just going to say that's it. You know, but I don't want to, if you guys aren't going to come and do it, then I'm not going to spend the money necessarily. So I just want to get you guys to start telling me you want to do it, and you're going to do it, because then you've missed your boat, and you're going to have to pay for it yourself next time around. Which I don't think this stuff matters that much. It's just a good thing to have on your resume. Can you get a job without it? Well, you're going to need your OSHA 10. But other than that, yeah, you can get a job without these. But everywhere I look, they want a NABCEP certification. And NABCEP doesn't really work for solar unless you've been doing it for a while, because it's like $600, $800. That's for people that already went to college and they're a project manager or something. They've never done any solar in their life, and they're just trying to pass the test so they can. That's not you guys, you know. these ETA tests are basically the same thing as a NAB set. They just cost a lot less, and they're really ETA's internationally recognized. So just people don't realize they're doing solar now. So yeah. What other questions about the test? Anything else? Let me show you something here before we get done, just so you can see. So if we go to fall, energy industry fundamentals, that's this course. We go into modules. There you can see the CWED test right here. So that is the actual exam. We don't want to do fall 20. We want to do fall 2021. No, fall 2020. That was last year, wasn't it? There's your practice certification exam right there.
We're looking at the book right now.
Thank you. I don't know why it won't switch. I'm going to do this. There you go. Okay, so this is, if you were in that class, if you were in Energy 100 last year, you should still have access to this. If you don't have access to your class, let me know, but I don't know why you wouldn't. But they do that stuff, and I don't know what's going on. But you would find out. It's hard for me to move this. I'd like to just grab it and drop it into your class right now. It just doesn't work that way, unfortunately. But I'll get it in there if that's what we have to do. But I believe all you guys have access to this. So you just need to come in here and let me know if you still have access to this course. You should come in here and just practice this CWED examination. So you're just going to come in here and just run through all these questions as many times as you can. Okay? If you do fairly well on it, after 6 months of not looking at it, you know you're going to be fine. But more practice on that exam, the better. But that's really all I got for you. And that's about the best thing. Or go back through all your tests and just read them over. Okay? That's what I've been hoping you guys have been doing for the last 6 months. I know you haven't, but that would have been helpful. Now you've got your fall wind power class. Okay? You should still have access to that. And when you click on that, I think it's at the bottom. There, I'm going to move it to the top. That's your ETA practice exam. Okay, for your wind. So that one right there, what we want to do is open that up. It seems like it's locked. So that's unfortunate. So we want to just make this like 20. I mean, I don't know if it'll let me. Hold on, I'm going to just try to erase this out, period. A lot of times that'll do the trick. And save it. Yeah, I'm still learning. Okay, so, well, that's ETA. Yeah, that's the right one. So that's not the CWED. That's ETA. They're both 71 points. That's interesting, isn't it? I don't know how that happened. But you're going to come in here and you're going to go through this wind turbine test. Now, there's some stupid stuff in here that you're not going to remember, like the first American windmill that was used to make electricity was known as the Glasgow wind machine. I know you're not going to know that, but that's on the test. So do that. Do that right there. Make sure you understand some of the silliness that's on these tests. So running through this thing right here, you know, this isn't my test. Somebody else made it. So there's some things in here that I think are weird, like the formula pi r squared is commonly used to determine the swept area of the horizontal axis wind turbine. Do you know that? Well, I don't expect you to know that. So this is not a time limit anymore. This is multiple attempts. Okay, I don't know why I did that before. We're not going to shuffle answers either. We want you guys to streamline this. Okay, so you need to let me know if you don't have access to one of those. Let's go back to the CWED one and let's make sure that
The
one's
ETA
good.
practice certification
Yeah.
exam is still unavailable. It
This
says
one
the
here
course
that
is
we just
no
looked
longer
at?
available as the course has been concluded.
Yeah, see, that's what I don't understand. Why they don't, okay. So I got to move those things, basically. So you got in here and you can't access this class at all.
No, I could bring up the modules and everything. I just couldn't
You can
Start
you
quick.
do it now? Let's see. I changed it. Refresh it and see if it works
Yeah,
now.
it doesn't work still.
Why? Because the course is ended.
Yeah, that's what it says. But
So it won't let you do these.
sure, I was allowed to do the other one in the energy class.
It did.
Let me
This
check.
exam. So what's this one do? So this is just walking you through it. That's just to tell you what you're doing. Okay. So they raised the price $5 on me. Okay. And then that is the exam. So you're saying it won't let you do it.
No, it won't let me do that one or the practice
Or the
CWED though either.
oh, neither one of them will work. Okay, bastards.
The OSHA 10 practice exam works because it's a PDF.
Oh, I see. Well, I might be able to just save it out as a PDF. But I'll that's what I needed to know, Cam, because that did make sense to me that you can still get in there, but you can't access this, even though the course. I don't understand that, but I guess they don't want you to do anything there for grid. I wonder if I could change this to something else. So let's see here. Type was a practice quiz. See, that's a practice quiz. That should allow you to do it. It's not a graded quiz. Yeah, I don't understand. Okay. Well, I'll work on getting that moved into something else. I have to figure out how to do that. All righty. Let's see here. I got a couple of questions. Okay. Yeah. Okay. Well, that's what I'm going to leave you guys with. Is there any other questions before I let you go? And then if those of you guys that want to stick around and ask questions about courses, you can. If not, then we need to put you on my calendar this week for a meeting. So if any of you guys want to put on there for a meeting, let me know, and I'll put it on there right now. If you need to think about it, we'll talk about it next class. But I'm going to let you go other than that. So you guys have a good day. And I'll let the rest of you get out of here. If you're sticking around, I'll check in on you here in a second. All right. Bye-bye.
Thanks, John.
Okay. David, where do you want me to put you on the meeting? Let me look at my calendar here. Let's see. Oh, my God. I'm getting destroyed. 20 freaking emails. Okay, let's look at my calendar. So tomorrow, Thursday. I'm with Adam on Thursday. Okay. So tomorrow, I'm pretty much open all day if you want to just meet with me, David. But I am, let me share my screen here. Let's see. Come on. Where'd you go? Give me 1 second. I get lost so easy. Okay. Okay, so when we look over here, see right here's my calendar. So all I need for you guys to do is just tell me, let's see. Okay. If you want to have a meeting with me, if you don't know, then we need to pick a time during the day. I'll be home all day tomorrow, working from home, since I don't need to be here. On Thursday, I'll be on campus in the afternoon. If you want to meet with me, and then of course I'll be on campus teaching all day Wednesday. But I want to go home and try to get a bunch of this emails and a bunch of this stuff done that I'm trying to get done and all set up. So I'll be killing myself tomorrow, but it'll be a good day for you to fill in one of these spots. If not, I could just try to run through the list. I know you need help, David, and any of you guys that need help, I'll be able to at least try to send you Tuesdays and Thursdays work. Okay. Well, you can see my calendar here. Is there a time you want to do, David? So in other words, On Tuesdays and Thursdays, unless I got a meeting here, you know, like from 1 to 2, I'm open. From 2:30 to 5, I'm open. You know, and then I'm open in the morning here, but I don't usually like to meet with people in the morning. I will. I don't have a problem meeting with you guys, but other people I don't want to bother me. This is when I'm trying to get your class stuff ready in between classes. Well, I'll just try to I'll try to work on some stuff for you guys tomorrow, since you're not sure when you want to meet, and then send you my recommendations of what to sign up for. I'm working on trying to get some classes to be converted over, like I mentioned before, to where you can do a full virtual class or a virtual blended. We've seen virtual blended lets you come to campus, but I don't even know if that's a thing we need to worry about. I think I'm not going to worry about it too much, but it's on my radar. I'm not sure what people are going to do this fall. Let's see, I got one more chat here. Yeah, the summer special projects course, I don't know about yet, and I do not think I am, but I will. I've got only you asking about it right now is the problem. So I'm still open to trying to do special projects, especially if there's more than just one of you guys that are interested in that. So that's on your radar. Yeah, not enough people is the thing. So that doesn't mean it can't be done, but it might be something we do in the fall instead. But I know summer makes sense, so I don't know what's happening this summer any more than you. So all we can say is let's do this, but nobody signs up for it, then we can't do it. So that's why I'm talking about the different options. That's still something I'm going to check on. Okay, I'm not completely against this whole special projects this summer. I still wish we would have done that and everybody signed up for it and we just came to campus and we all just had a good old time wiring things up all summer. It'd be a great summer. All right. Well, let me work on anything else that you guys need. Get that stuff ready for you. And then I'm just going to get out of here. Is there anything else you guys need before I go? Don't see any other chats from you guys. So I'm going to roll on out of here, and I'll work on this stuff tomorrow, and I will see you guys later. About 3:30, about 2 hours in. Just get that homework done, and I'll talk to you guys on Wednesday if I don't see you before then. I'll try to send some emails. So have a good day, and I'll talk to you soon. Bye-bye. No problem, David. Bye-bye. I have no